In this video, we will recall introductory matrix algebra. An m cross n matrix A is written as a regular array of n elements. So we denoted it by A of ij, Aij. So I denotes the row, J denotes the column. If the number of rows is equal to the number of columns, then the matrix is called as square matrix. A square matrix A is symmetric if it is equal to the transpose of its own. So AI, that means Aij equal to Aji. It can be antisymmetric if A equal to minus of A transpose. So that means Aij equal to minus of Abi. So the unit matrix is denoted by Kronecker delta, and here this Kronecker delta symbol denotes like it is 1 only if I equal to j, otherwise it is 0. The trace of the matrix A can be written as sum of indices I1, 2, 3 of Aii in terms of the elements of the matrix. One can also write the determinant of the matrix in terms of elements using Levi-Civita symbols. The condition that determinant A is not equal to 0 is necessary and sufficient for the existence of the inverse. So a square matrix is said to be orthogonal if the transpose itself is its inverse. So that gives determinant of that matrix is plus or minus 1. So that denotes the matrix is orthogonal. A square matrix can be orthogonal. So if you take the transpose, multiply it, you'll get identity operator. So we use the summation convention here. If any index repeats in the expression, then we have to take the sum. That's the rule. And we can write the we can make use of this this convention and write like multiplicating two matrices, square matrices AB. We can write it as Aik Bkj. So k is repeated here and you have to take the sum. So let's say if Q is our orthogonal matrix, Q transpose can be written as Qi Qij and Q transpose of Jk. Then we can write it as Qij and Qkj. So that means it is equal to delta Ik. So that what you get. And also trace of AB turns out to be Aik and Bki, and because you have Aik and Bkj and you take only the diagonal elements, then you will get again the I for indices. So trace of ABC will turn out to be Aij, Bjk and Cki. That gives you the trace of multiplication of these three matrices. So for we have some expression for Levi-Civita symbols. So these are the useful relations for Levi-Civita symbols. So Eijp and Eijq gives 2 of delta pq, and Eijp ERSP gives delta IR delta JS minus delta IS delta JR. This is the relation between the Levi-Civita symbols and the Kronecker delta. And we can write the determinant in terms of the elements of the matrix A. using Levi-Civita symbols without using any summation symbol, because if any index is repeated, you have to take the sum. So now let's take eigenvalue equation. So now we need to solve Ax equal to lambda x. We know only matrix A. We need to find lambda, a number, and x, a vector. So we call these as lambda as eigenvalues, x as eigenvectors. So given a square matrix A, we need to find eigenvalues and eigenvectors. To do that, first thing to notice is that we have to solve this equation, a minus lambda I x equal to 0. You are just taking the lambda x to the other side, so you'll get a minus lambda I x equal to 0. If a minus lambda I has inverse, then we can multiply this equation with a minus lambda inverse and you will get x equal to 0, which is a trivial solution for this equation. To get non-trivial solution, a minus lambda I should not have inverse. So what is the condition for a minus lambda I should not have the inverse? The condition is determinant of a minus lambda I should be 0. Then that matrix does not have inverse. So we impose the condition that determinant of a minus lambda I is equal to 0. So the eigenvalues are lambda 1, lambda 2, lambda 3. So we will get an equation for this matrix. Let's say we solve that matrix and we get the eigenvalues, and it can be written as the solution lambda 1 minus lambda 2, lambda 1, lambda 2, lambda 3 are the solution eigenvalues. So solving the equation, you get these polynomial, you get the solution lambda 1, lambda 2, lambda 3. If you consider lambda is equal to 0, then we get this relation. Determinant is determined by the matrix is determined by the product of the eigenvalues of that matrix. So one can also show that the eigenvalues are real if you consider A is a real symmetric matrix. So you just have to take the complex conjugate of the eigenvector, take the complex conjugate of this equation, and act the first equation by complex conjugate of the vector and the second equation from the right to the direct eigenvector. Then you get this relation. We know this sum cannot be 0, so this must be 0. So lambda 1 is turned out to be the complex conjugate of its own value. So what does it mean? It has only real components. This shows that the eigenvalues of the real symmetric matrix are always real. So now what we have is, and the eigenvectors, what we can show is that eigenvectors corresponding to two different eigenvalues are always orthogonal. That's a easy task. We can do it from here. Take two equation, act it other one corresponding the different eigenvectors. Then the first equation matches with the second, so you have to equate them. Once you equate them, then you can get that you have only the choice to take the eigenvectors as orthogonal, otherwise it cannot be 0 to satisfy the equation. So now if lambda is an eigenvalue, then we can construct this vector P, matrix P, which consists only as the eigenvectors of the matrix A. Then we writing in terms of like P A P transpose, then you will get only the diagonal elements of with the eigenvalues of the matrix chosen A. So this is how we diagonalize the real symmetric matrix. So writing the eigenvectors along the columns in one of the matrix, act that matrix chosen matrix on it, and take the transpose of the matrix constructed, then you get the eigenvalues along the diagonal. Next thing is the Cayley and one more thing, if we have lambda as an eigenvalue of the matrix A, you take the A square, act it on the corresponding eigenvectors, then you can find that lambda n is the eigenvalues of matrix an with the same x as the corresponding eigenvector. So what Cayley-Hamilton theorem says that the characteristic equation which we have constructed from determinant of a minus lambda I, this is also satisfied by the corresponding square matrix what we have considered A. Just substitute in the place of lambda in the characteristic equation by the matrix A itself, then also it satisfies the equation. This is what Cayley-Hamilton theorem says. So what is polar decomposition theorem? A matrix A is positive definite if all the eigenvalues are real and positive. So a positive, this theorem says that a non-singular square matrix can be expressed using orthogonal and positive definite symmetric matrices. This is polar decomposition theorem. So to do that, whatever you have a matrix F, here it is F, so you construct F transpose F and then construct corresponding P vector to it, like here what we did in the case earlier to diagonalize. Now you have F transpose F as the C, so you diagonalize, you get the square of the matrices, square of the eigenvalues, sorry. So construct P, and with this P now construct U, and this U matrix is symmetric and positive definite. With this U, you can construct R, and one has to show that this R is constructed from here as Fu in minus, and R is shown to be orthogonal. So from this theorem we can show that a square non-singular square matrix can be expressed using one orthogonal matrix and a positive definite symmetric matrix. Thank you.